November 2025, Rheinmetall unveils its latest Leopard 2A8 configuration. Improved chassis, cutting-edge suspension, highly developed torsion bars, top-tier German engineering. But take a really close look at the specifications, the suspension principle, the torsion bars themselves, the fundamental design. It's 82 years old, November 22nd, 1943. The Daimler-Benz factory in Berlin-Marienfelde. Professor Ernst Lehr completes his revolutionary double torsion bar system for the Panther tank, 250 millimeters of suspension travel, 40% better than any Allied design. A mechanical masterpiece that forever altered the physics of tank suspension. Today in Ukraine, T-55 tanks with torsion bars are battling Leopard 2 tanks with torsion bars. American M1 Abrams use torsion bars. Russian T-90Ms use torsion bars. Chinese Type 99As use torsion bars. Over 350,000 tanks produced worldwide since 1945, all based on a concept Professor Ernst Lehr perfected in Berlin in 1943. No royalties were ever paid, but the technical dominance is absolute. 82 years later, every modern tank on the planet uses a German design from 1943. Today, I'll show you the documented technical lineage, from Ernst Lehr's drafting table in Berlin, to Aberdeen Proving Ground in Maryland, to every battlefield in the world. The story of how a German professor invented a technology so perfect it never needed improvement, only replication. This is the story of the Panther's torsion bars and how they conquered the world. 1942, Eastern Front. German tank commanders report a devastating problem. The new Soviet T-34 tank isn't just better armored and armed, it's more mobile, much more mobile. The reason is technically simple: Christie suspension, large suspension travel. The T-34 can travel at 55 kilometers per hour over terrain that forces German tanks to crawl. In combat, mobility means survival, position, tactical advantage. The German responses of the time, Panzer III and Panzer IV, use leaf springs. American Shermans use vertical coil springs. Both systems have fundamental weaknesses: limited suspension travel, complex maintenance, heavy components. Albert Speer, Reich Minister of Armaments, issues an order: new medium tank. Mobility like the T-34, armor better than the T-34, armament superior, and the critical element, a suspension that surpasses everything that came before. Daimler-Benz gets the contract. Professor Ernst Lehr leads the suspension team. The challenge is brutal. A 45-ton tank has to move like a 26-ton T-34. But physics are unforgiving. More weight needs more suspension travel. More suspension travel needs longer springs. Longer springs need more space. More space means a wider tank. A wider tank means a bigger target. A bigger target means more hits. More hits mean more dead crews. The problem is unsolvable. With conventional engineering, Professor Lehr has another idea: torsion bars. Long metal bars that twist under load and then spring back. The British use them in some designs. The Soviets are experimenting with them, but no one has perfected them. The reason is mathematically complex. A torsion bar has to be long enough to provide sufficient suspension travel, but a tank is only as wide as its inside allows. For 250 millimeters of suspension travel, the minimum that Lehr calculates as necessary, you'd need a torsion bar almost 2.5 meters long. The Panther's hull is only 1.85 meters wide, inside. Mathematically impossible. Here's Lehr's stroke of genius. He folds the torsion bar, literally. The system works like this. The first torsion bar runs from the swing arm across the hull, 1.85 meters. It connects to an angled lever. The angled lever connects to a second torsion bar. The second bar goes back across the hull, another 1.85 meters. The two bars work together. The effective length doubles, 3.7 meters of torsional action in a 1.85 meter wide hull. The physics are elegant. The engineering is brilliant. The results are revolutionary. 250 millimeters of suspension travel per wheel. 8 wheels per side in the interleaved road wheel arrangement. This means the Panther can absorb 25 centimeters of vertical movement at 45 tons, at 55 kilometers per hour, over terrain that would destroy other tanks. Compare the numbers. Sherman M4, 150 millimeters of suspension travel. T-34, 180 millimeters of suspension travel. Panther, 250 millimeters of suspension travel, 40% better than Allied designs, 28% better than Soviet designs. But it's not just about numbers, it's about physics. A tank with better suspension travel can drive faster over rough terrain. Driving faster means better position. Better position means first shot. First shot means survival. A tank with better suspension travel can shoot more accurately while moving. The stabilization is better. The weapons platform is calmer. A calmer platform means a higher hit probability. Higher hit probability means more destroyed enemies. A tank with better suspension travel has a longer lifespan for its running gear. Fewer shocks mean less wear and tear. Less wear and tear means less maintenance. Less maintenance means more time in combat. More time in combat means more tactical value. Ernst Lehr's double torsion bar system solves all three problems at once. The first Panthers leave the production line in January 1943. 1,768 kilometers of test drives, extreme conditions, hills, trenches, mud, snow. The suspension exceeds every expectation, but specifications on paper and reality in combat are different universes. July 1943, Battle of Kursk. The first 200 Panthers see combat. The results are mixed. Engine problems, transmission failures, but the suspension is perfect. Crews report, the Panther drives like a sports car, over terrain that slows down T-34s, over obstacles that stop Shermans. The mobility is extraordinary. The tactical flexibility is superior. Allied commanders notice immediately this new German tank moves differently, faster, smoother, more dangerous. The first captured Panthers reach Allied testing grounds in the fall of 1943. Aberdeen Proving Ground in Maryland receives Panther No. 4 in May 1944, captured in Italy, shipped to America for detailed analysis. The American engineers are professionals. They dismantle every centimeter: engine, transmission, armament, and of course, suspension. The test report is 124 pages long, declassified in 1952. Publicly available today in the National Archives, page 67, section on suspension. The American verdict is clear. Quote, "The Panther's torsion bar suspension system is the most advanced we have analyzed. The double bar mechanism allows for exceptional suspension travel in a compact space. The resulting mobility surpasses all comparable American or Soviet designs by significant margins." Page 69. Technical specifications. The Americans measure everything. Torsion bar diameter, 60 millimeters. Material, chromium molybdenum steel. Heat treatment, hardened and tempered. Suspension travel measured 248 millimeters, within 2 millimeters of the German specification of 250 millimeters. Page 71. Comparison with the M4 Sherman. The American tank uses vertical coil springs. Suspension travel, 152 millimeters. The report states, Sherman suspension delivers 39% less suspension travel than the Panther. This results in significantly reduced off-road speed and increased crew stress over longer operations. The Americans understand exactly what they are seeing. Top-tier German engineering has solved a mechanical problem that Allied engineers considered unsolvable. And the solution is so elegant, so efficient, so perfect, that it cannot be improved, only copied. But here is the critical question, a question that will define the next 80 years. If the Allies understand in 1944 that German torsion bar technology is superior, why don't they immediately change their own designs? The answer is complex, partly production. They have already built 50,000 Shermans with coil spring suspension. Retooling production lines would take months, partly confidence. The war is going well. Why change what works? But mainly it is pride. American engineers believe they can do better. They don't analyze German technology to copy it. They analyze it to surpass it. That is the plan. 1944, 1945. But then the war ends, and everything changes. May 1945. Germany capitulates. Allied troops flood German factories, Daimler-Benz in Berlin, Henschel in Kassel, Krupp in Essen. They don't just find tanks, they find blueprints. Technical drawings, test data, production documents, decades of German engineering, documented, archived, ready to take. Operation Paperclip for rockets is famous. 600 German rocket scientists brought to the USA, but there was also Operation Matchbox and Operation Epsilon and a dozen other programs without code names, all with the same goal: German technology, systematically studied, systematically appropriated, systematically integrated into American production. Tank technology is a priority. The Soviets are no longer allies. They are future enemies, and Soviet tanks already use torsion bars. Inferior torsion bars compared to German ones, but torsion bars nonetheless. The American tank development plan changes overnight. All future designs must have torsion bar suspension, but not just any torsion bars. German torsion bars. Professor Ernst Lehr's system. There's just one problem. Ernst Lehr has disappeared. The search for Professor Lehr is a story in itself. He worked at Daimler-Benz until April 1945. Then his trail goes cold. Some reports say he went west to meet American troops. Others say he hid in southern Germany. Still others claim the Soviets found him first. The truth remains unclear, but his drawings remain, his calculations remain, his invention remains, and the Allies take it all. 1946, Aberdeen Proving Ground starts Project TT-17. TT stands for Tank Technology. 17 is the project number. The goal is precise: a new American tank with German suspension technology. The team consists of 23 engineers, led by Harold Moore, a graduate of MIT. They have unlimited access to captured Panthers, to German documents, to test data, to everything except Ernst Lehr himself. They study every detail: the torsion bar geometry, the bell cranks, the swing arm linkages, the materials, the heat treatment, the interleaved road wheel integration, and then they make a critical decision, a decision that changes the course of global tank technology. They simplify the design. Lehr's double torsion bar system is brilliant, but it is complex. 2 bars per wheel, 16 bars per side, 32 bars total, plus bell cranks, plus complex assembly. Production is expensive, maintenance is difficult. The American engineers have another idea. Why not a single, longer torsion bar? Modern metallurgy allows for stronger steels. Stronger steels allow for thinner bars. Thinner bars allow for more torsion per length. A single bar across the full hull could deliver the same suspension travel as Lehr's double system. With half as many components, the math works, the physics works, the tests work. 1949. The M46 Patton enters production, the first American main battle tank with torsion bar suspension, single bar design, 230 millimeters of suspension travel. Not quite 250 millimeters like the Panther, but damn close. The M46 sees its first combat in Korea, 1950 to 1953. Crews report the mobility is excellent. The tank can keep pace with Soviet T-34-85s. It can maneuver faster than the old M4 Shermans. The suspension absorbs artillery strikes near the tank. The weapon platform remains stable at high speeds. The M46 Patton becomes the blueprint. M47, M48, M60, all use single-bar torsion bar suspension, all based on the concept that American engineers developed from Ernst Lehr's captured drawings. But the Americans are not alone. The Soviets have their own Operation Paperclip, Operation Osoaviakim, October 22, 1946, 3 a.m. Soviet NKVD agents knock on 2,500 doors in the Soviet occupation zone. German engineers, German scientists, German technicians, all with a choice: voluntarily come to the Soviet Union or forcibly go to the Soviet Union. 6,000 people, engineers plus families, are on trains heading east by noon. Some of these engineers worked on tanks. Some worked specifically on suspension. They bring knowledge. They bring documents. They bring German methods to Moscow. 1947. The Morozov Design Bureau in Kharkiv begins work on the T-54, the successor to the T-44, a tank that will define Soviet doctrine for the next 40 years. The T-54 uses torsion bar suspension, single bar design like the Americans. But with Soviet modifications, here is the irony. The T-44, the predecessor, already used torsion bars. Soviet engineers had been experimenting with them since the late 1930s, but the T-44 had problems: limited suspension travel, unreliable bars, broken swing arms. The solution comes from German documents, German metallurgy, German heat treatment, German geometry. The T-54 isn't a direct Panther replica, but it's based on German principles, German calculations, German tests. The proof is in the numbers. T-54 suspension travel, 250 millimeters, exactly like the Panther, not 180 millimeters like the T-34, not 220 millimeters like the T-44, exactly 250 millimeters, the number that Ernst Lehr calculated as optimal in 1943. Coincidence? Or systematic appropriation of top-tier German engineering? The Soviets don't give credit. They don't cite sources. They claim everything is Soviet innovation. But the numbers don't lie. 250 millimeters isn't a random coincidence. It's a calculated optimization, an optimization that a German professor made in Berlin, an optimization that Soviet engineers adopted from captured documents. The T-54 goes into production in 1947. By 1979, the Soviets produced 27,500 T-55s. The improved version. Czechoslovakia produces another 10,000. Poland produces 8,000. China produces over 10,000 of their Type 59 variant. North Korea produces untold thousands. Total production of the T-54 and T-55 family, over 100,000 tanks, more than any other tank in history. Every single one with torsion bar suspension, every single one with 250 millimeters of suspension travel, every single one with a system based on German engineering from 1943. And that's just the beginning.